might be able to do that. Okay, so at the end of yesterday, we started talking about functions within C. And I introduced an example in which we were using call by value. So call by value refers to the manner in which variables or arguments are passed to the function. So there are two methods that can be used. So the first is call by value, which we talked about yesterday, and the second is call by reference, which I'll introduce today. So in call by value, if we remember to our example from yesterday, we had a function called mySimpleFunc by value. Let me expand that so it's easier to read. And I'm just going to put open close parens here. It obviously had a couple of arguments that we passed, but just for quick reference, I'm going to just use open close parens to make it clear that it's a function, but I'm not really concerned about the arguments quite yet. And then we had a second function. We actually had more than just two within the entire file, but in this discussion, let's just consider these two. And we had our main function. And our main function is needed by every C program. So execution begins in the main function, and the first function that we called after initializing a couple of variables, if you recall, was mySimpleFunc by value. And within our main function, we had a couple of variables that we were passing. That looks better. That we were passing to mySimpleFunc by value. And those were, let me just go ahead and get these drawn. Okay, and the two variables here were what? Does anyone remember, or does anyone have it pulled up? Let's take a quick look. So we were just passing I and X to mySimpleFunc by value. So let's get that entered in. I and X. And then within the actual function that we're calling, we have two additional variables, which we had called iloc and xloc. Okay? And so if we look back at the function, these are listed in the exact same order that we're calling the function with when we pass in I and X below. So right here, notice that the order of the arguments is I followed by X. And so each of those still correspond to the order of the arguments listed in the function definition above. But what is important to realize about when you're passing arguments in this way is that there's actually a separate copy. So these variables, they don't persist outside the scope of this function. Okay, so there's actually a separate copy in memory for these variables that are created. And the value from I and X is copied in to that memory address. But the result of that is that when we modify iloc and xloc, as we do in these two lines, those don't propagate out to main. So the value of I and X is actually not being changed. Those values remain unchanged when we pass by value. Okay. To contrast that, we can use pass by reference. And when we use pass by reference, essentially what it allows us, it gives us the ability to change the value of a variable that's initialized and defined outside the scope of that function. All right, so I'm going to go ahead and write this out, even though we haven't looked at this function yet, but it's called mySimpleFunc by reference. And then we also have main. And let's see, can I do this? This might be a lot easier. Yeah, great. Oops. What happened to my I? There it is. Okay. This down here. That's here. I'm fully aware there's probably an easier way to do this, but I didn't really take enough time to research alternatives. Okay. So within main, we're again going to have X and Y. Or I'm sorry, I and X from main that we're going to be passing to this function. So if we scroll down, right here is where we call my simple func by reference. And so now, rather than just listing the name of the variable, we're putting that funny-looking ampersand symbol in front of the name of the variable. And from yesterday, can anyone tell me what that's actually doing?
You're passing the address?
Yes, correct. So you are, in case you didn't hear that, you're passing the address of that variable to this function. Okay. And so if we which makes sense intuitively. If our goal is to actually change the value of that variable so that it persists outside the scope of this function call, then it needs to know where that variable is stored. So we're going to pass that address, and when we scroll up to my simple func by reference, we will see that within the argument list, we're now declaring these as pointers. Okay, so if you remember from our discussion yesterday, pointers, the type of it looks like I've disconnected here, but I'll just keep going forward. The type of a pointer is essentially, its type is the address of a particular type within C. So in this case, we're declaring a pointer that's going to be pointing to an integer and calling it iPointer, and a pointer that points to a floating point, a single precision floating point number, and calling it XPointer. All right, and so the type is going to actually be consistent because we're passing in an address of these two variables, and a pointer's type is an address. So that should also make sense. And so now that we have an address, we can't directly manipulate. Well, you can directly manipulate an address, but I wouldn't advise it. But instead, what we want to now do is modify the value that is stored at that address. And so if you recall from yesterday, the way we do that is we do something called dereference the pointer. And so we use this asterisk in front of the pointer name, and then we're going to increase the value that iPointer is pointing to by 101, and we're going to multiply. We're going to scale this value that XPointer is pointing to by a factor of 14.6. And then below, we're also, just for consistency with our my simple func by value, we're also going to go ahead and multiply these two values together. And remember, we talked about typecasting yesterday. When you're performing operations on two different types, you have to cast one of the types. So here we're recasting iLoc as a floating point number, multiplying those together, and then returning the value yLoc. And so note that this is another way to get a value back from a function is to return it. But another way is if the variable is already defined, if you've used it in your main function and you still need to hold on to that variable, then you can pass it by reference. So there's a couple different ways to do it. So if we go back to our sketch pad here, the way we would represent this is with now we have, instead of iLoc, we have iPointer, and we have XPointer. And those are actually now pointing to this address space outside of the scope of this function. So that's the really key part. They are mapping all the way out here to this value's address. And the same with iPointer. It's actually pointing to this address space. And so when we dereference this variable, it's giving us the value back that's stored at the address that we're pointing to. All right, so let's go ahead and compile that. Although I don't know if there's a network blip or what, but I'm going to have to reload this page. Maybe I can refresh it actually. Let me try that. Reload. There we go. All right, so functions.c is the example we're looking at. So I'm going to go ahead and build it. And just to glance over this, to think about what we'd expect the values to look like. Initially, we're printing the value for I, x, and y. If you recall from yesterday, I and x did not change. They were still set to these initial values. Whereas y, we returned that value from this function. So it picked up the value that we passed back. And now we're also going to, we are going to run, call mySimple by reference, passing the address of both of these variables. And so now we should expect the value of I and x to have actually changed. So let's see if that's what happened. Yes, great. So if you can see down here in this tiny font, so x and y now have different values. Although y, no, oh, I'm sorry, I and x have different values, and y is the same as it should be. Any questions about any of that? How kind of pass by reference works, or how some of the pointer bits work? And just to give you a heads up, so if you were to do this, so if you were to not dereference that pointer, try to increment it, it would compile. Let's see what it gives us. This is going to be interesting. 22, so it's still equal to 22. So we didn't actually successfully change the value of I. So you just want to be careful that you're actually dereferencing it and getting the value that it's pointing to. Also note that if you forget that star within your function definition where you're listing the arguments, you'll get you'll get an error. And that error is actually pretty instructive. It's basically complaining about the fact that the types between the function call and the function definition are inconsistent. So invalid type argument of unary star have int. So it's maybe sounds a little strange, but that's essentially what it's trying to communicate. Maybe this meant, yeah. Warning, passing argument 1 makes integer from pointer without a cast. Enabled by dPoint. Here we go. Here's the most helpful. Expected int, but argument is of type int star. All right, so that's telling us concretely what the problem is. And int star is an address, whereas an int is just an integer. All right. So that's one that you'll probably see during the course of the semester. It's a pretty common one to forget to include that asterisk to specify that it's an address. The last thing that I want to discuss, and this is really important, a really important concept in C, is that arrays are sort of a special type within C. So arrays are passed by reference by default. Okay, so I want to underline that, or yes, I'd underline the whole thing, but maybe can I, well, anyways. So they are passed by reference by default. So anytime you are passing an array to a function, when you modify that array within the function, those changes will propagate outside the scope of the function. All right, and so what you really just kind of detailed you have to remember is that if you have an array, let's say let's just int my array 10 or something like that. When you are passing, well, that's not true. In general, my array is the same as writing, okay, so this is really, really important. I put a star. What does this do? Okay, I'm going to put a stars around this statement. It is very important that you remember this. So what this means is that when you are passing an array to a function and you just list my array, which is what you generally do, actually that's just kind of like an alias to the address of the first element, the very first element in the array. So it's pointing to the very first element within that array. All right, so if you had like it's just a really poor way to do this, I'm sorry. So if you had an array of a handful of elements, and you pass something like my array, it's just pointing to that very first element within the array. So if this is like, I'm going to call this, let's just go ahead and be consistent, my array 0, my array 1, and so on. When you pass this name, when you refer to the array just using the name without any brackets at all, then that is shorthand for writing, give me back the address of that first element in the array. And another really, really important detail is that arrays are contiguous in memory. And that's actually what makes them so performant, is that the compiler can make a lot of assumptions when it knows that it's guaranteed that each element in the array is just going to be in the next memory element. So when they're mapped in memory, it's just one after the other, after the other, after the other. That makes life a lot easier, and that makes that's why arrays in general, the performance of them are better than something like a linked list, where each element of the linked list does not necessarily have to be contiguous in memory. They can be scattered about, and then they just have pointers that essentially point to the next element in the list within each element of the linked list. So that, so that's just a point I wanted to stop and stress here. So as an example, let's say we have a 2-element array and we initialize both elements to 0, and we're going to print the value before and we're going to print the value after calling this function called modify array. And within the array, all we are doing is just changing the values to 5 and 12. And a really important detail here is that because of this starred statement right here, that my array is just shorthand for the memory address of that first element. When we write our function definition and we're passing in an array, it's always going to be a pointer. Again, it needs to be an address that we're actually passing in. Right? So we're going to call that function and then print the values out afterwards to convince ourselves that the updated values actually propagated outside of the function scope. Yay, and indeed it does. So before the function call, my array was 0 and 0 for elements 0 and 1 respectively, and then updated to 5 and 12. So that's an extremely simple example, but I think it's one to conceptually understand how it works, because arrays are going to show up all over the place in this class, and it's important to kind of understand and comprehend how to pass those between functions and to know what kind of behavior to expect. Any questions about that at all? Okay. You guys are so close to being C experts. So let's move on to the next example. So we're going to talk about structures. Structures also show up a lot within C in general, and within this class, they're certainly going to show up a lot. So a structure is, let's see if I have any notes here. I don't really have any notes. So the oh yeah, I do. Okay, good. So I've got a couple of things to say here. So I'm going to go ahead and erase this. Structures, or structs, usually just called structs for short. Okay, so a structure is the closest thing to objects in C. So if you've never done object-oriented programming, don't worry. So an object, you can just think of it as it bundles groups of related variables together into a single variable. And this turns out to be really convenient. One of the big reasons is that it simply, it's going to sound very simple, prevents programmer from needing to pass a huge number of variables to functions. So if you had, if you define a function and you find you need like 15 or 20 values from within your main function, option A is to actually write out each of those arguments, each of those variables that you've defined. But that turns out to be a huge pain. But more importantly, it's very prone to error. So you can introduce a lot of bugs that way if you get these epically long argument lists that you're constantly having to keep track of the order of those arguments and not mix those up. So rather than doing it that way, generally the preferred method is to bundle together related, and usually you'll find that those variables are related in some way. They help describe some larger object or the characteristics of some object in some way, and so it makes sense logically to actually bundle those together into a structure. Okay, so the way we define a structure is the following. So in this function, something that's a little bit different is that this is kind of the first time we've defined anything outside of the scope of any of our functions. So you don't have to do it this way, but it's often a lot more convenient to put something like a struct definition kind of outside the scope of all your functions, so that all your functions are aware of the definition of the struct. It's more conventional to put this like in what's called a header file. So you define, if you remember from day one, we talked about header files. This is the standard input-output header file where printf lives, but we can also define our own header files and stick definitions like this within that header file, and then include the name of that header up here. And we'll see that within class. So within this struct, you can declare structs in a couple of different ways. I prefer using the typedef method. So what we're actually doing here is we're defining a new type. And so by type, I mean something like an int or a float or a character. We're actually defining a new type, and we're going to call it student. Okay, so we type typedef struct, and then we use our curly brackets to enclose all of the data that we're going to put within that struct. And the name of the type is student. And so within this type, we have 4 different variables. We have a pointer to a character, which is where we're going to store the name of the student. We'll talk about that more later. We're going to store the age of the student in years, the height of the student in inches, and grades. So the grade on 10 assignments for the student. Okay. So if we come down here to main, we're actually going to define our first student, and we're going to call that student Nikki. And so again, student is just like any other type, so we declare it like any other type. We start with the type name, and then we give the variable a name. And so the name in this case is going to be Nikki. And then we're going to initialize the values of our struct. And so to access elements of a struct, use this dot notation. If you're coming from Python, this probably looks familiar and pretty intuitive. If you're coming from Matlab, this might look a little strange, but all it's doing is saying give me. It's referring to an individual element of the struct. And so we can, once we've done that, the dot notation followed by the variable name within the struct, we can assign variables just like we would normally. And then we are going to also assign the height as well as the age, and then we are going to assign some grades. So let's say that Nikki is just an overachiever and she aces everything. I mean, she gets, not quite aces, but she gets a 98 on every single assignment. So once we've done that, let's first go ahead and print the struct to be sure that we got back our values in the way we expected. And so we've defined a function here called print struct, which is right here. So it's right below our definition of our student type. So one thing that we haven't seen yet is, and this is really common, especially when you're just printing the value of variables, is to return a void type. So when you define a function, if you're returning void, it means you're not returning anything. And so there's no need to have like a return foo here. Just note that when we call that function, that means that we can just call it without having to assign a value to it at all. Sorry, right here. So we are going to call this function right here. And within it, we're passing the type, and the type is, again, student. And the local name of the student type here within this function is going to be called oneStudent. All right, and so all we're going to do is use printf to print off all this information. So this should all look pretty familiar. We haven't talked about formatted output within printf statements. All this is doing is specifying how much precision we want. So it's telling us the total number of columns we want to print for that number, as well as the number of columns after the decimal place. So it's going to give us 6 columns to print in, and 3 of those can be after the decimal place. And then we're going to print the grades as well. And at the very end, we are going to change the age of the student. And then we are going to print the struct once again, just to convince ourselves that, although we're, yeah, okay. So I've made a note here, and this is the same as, a struct is the same as just any other normal type, excluding excluding arrays, in that if you want the changes to a struct to propagate outside the scope of the function, you need to pass it by reference. And unlike an array, it is not passed by reference by default. And so when we update the age at the bottom of this function, because we did not pass the address, this age is not going to propagate out to our main function. All right. So next, we are going to actually modify the struct. So we have another function called modify struct, and notice now that we are passing this by reference, which intuitively should make sense, because if, like I just said, if we need to modify the contents and to have those changes make it into main, then it's important to pass that variable by reference. And so within this function, note the asterisks here because we're passing an address. We're just going to update 3 random grades. The thing that we've introduced here that is new is this interesting looking syntax right here. And so this is when we dereference this is the equivalent of writing the following, dereferencing this pointer, because remember we have an address, so we need to dereference this to update the value that's stored at that address, followed by a dot and grades 0. So that's what this means. It's just a shorthand way. You can actually write this out every time you want if you really want to, but it's a little more concise and readable when you're dealing with pointers to structures to use this notation, just this pointer notation right here. It's just a dash followed by a greater than sign. And then finally, we are going to print the new values of the structure once we've updated the values. So looks like I've got disconnected again, so I'm going to need to refresh this again. Are there any questions while I'm doing that? Okay. Becca, do you have a question? All right. Becca, I see you have your mic unmuted, but I'm not hearing anything. I'm not sure if.
Hear me now?
Yep, I can hear you now.
If you don't assign values to the variables within student, will that cause any errors?
Within. Oh, okay. So you mean like right here?
Yeah.
So if I don't initialize any of them, no, it won't cause errors. It'll give me a warning, I think, and just tell me that. We can try. I think it'll just tell me like, hey, you declared this variable, but you never actually did anything with it. Although, because we're passing it to functions here, it probably won't complain. But if I were to declare that and not reference that variable or use it in any way throughout the rest of the program, then it would just give me a compiler warning.
Okay.
Was that what you're asking?
Yeah.
Okay, great. All right. So let's go ahead and build these and run structures. Okay. So recall that initially we're just printing the initialized values. So Nikki's age is 19. Her height is 64 3/4 inches. And she's making awesome grades. Good job, Nikki. And then after we've modified the values, we do indeed see that those changes make it out to main, which is great. That's what we expected. So the first grade is now a 72. Not so great, Nikki. Then an 81 and an 85. So I think she still has held on to her A average, but yeah, she had a few slip-ups there. And so also note that, recall we tried to update this value here. We updated the age, and that remained unchanged. So when we called the function a second time, it's pretty clear that that age never actually changed. So again, that's because we're passing by value instead of passing by reference. In general, you use pass by value if you are not modifying the contents of a variable, and you pass by reference otherwise if you are modifying it. Although there's an exception to that. So who can think of any other possible disadvantages of using pass by value over pass by reference? Any guesses?
I mean, you occupy more memory space.
Yeah, you occupy more memory space. And that becomes really important when you are dealing with very large variables. You're not just occupying that space, but you are also having to copy everything over. So that can be a kind of what we would call, quote unquote, an expensive operation in that it takes a lot of computing time. to actually copy that data into the separate space. All right, so we got about 25 minutes, and I'm going to go a little faster through these last three examples. These are things that are important and will show up, but I would say the most important things we've talked about, covered in general, that you understand are pointers, structs, and pass by reference versus pass by value. If you feel like you've mastered those and you get those, then you are set up. You're good to go to do well, I think, in this class. But these last ones are also important, and they'll definitely show up, especially dynamically allocated arrays. So let's first talk about pass command line options. So often it's convenient to pass options to your variables through the command line, so you don't have to recompile your program. So the way you do that within C is that you, instead of including no arguments to your main function, you include these two. And you can essentially, actually that should have a space right there. Although this will compile. So I should note that you'll sometimes see pointers used or declared like in this way, with the asterisks actually sort of attached, prepended to your variable name, and you'll also see it with a space. They'll both compile and they both work fine, so don't let that trip you up. But in this case, we're actually including two asterisks, which if you think about this too hard, your brain might explode. But what this is essentially a pointer to a pointer. So I wouldn't really worry too much about trying to conceptually understand that, but suffice it to say that a pointer is just like any other variable. It just happens to store an address, and so you can also point to a pointer. So that's what this is doing. And so pointers to pointers show up when you need to do something like a two-dimensional array, because you need to create like not only a row but a column of data to refer to. So, but let's kind of leave it at that, and we can revisit it later if there are any more questions. So what this is going to do is essentially argc will be assigned the number of arguments that get passed from the command line, and argv will be an array that contains the actual arguments that were passed. And the arguments will be essentially strings, not strings per se, but like arrays of characters. And so we have to convert those arrays of characters to the appropriate type later. So the way this generally works is within this program, I'm initially going to point the number of arguments that I'm passed. And you generally write right off the bat some logic to ensure that you're getting the number of arguments that are needed for the program to run. So here I'm saying if I don't receive 3 arguments, then basically exit, print like an error message and say, this is what I was expecting, please try again. Notice that this is a 3 and not a 2. The program's expecting 2 arguments, but argc considers this an argument as well. So the name of the program, the / program name, is technically considered an argument too. So in this case, we want to look for 3, even though we're accepting 2 command line arguments. All right. And so next, I'm going to argv captures each argument in an array of characters. So here, I'm just going to loop over argc and print each of those strings or arrays of characters from the command line. And then finally, the last step is to convert those arrays of characters to the appropriate type. And so in this case, we have to know what we have to specify within the documentation and within error messages what type we are expecting to receive. And you can do some additional sanity checks, but here we're assuming that the first argument is an integer. So we're using this function called a2i, which is going to take a string and convert it to an integer, and then we assign it to myArgInt. And then we do the same for myArgFloat, except now we're using a2f, where f is for floating point number. Note that we need an additional header file. So a to I and a to f are functions that are defined within standard lib.h. All right. So we've already built that, so I'm going to go ahead and run it. Pass command line options, and you'll notice that I get that error message, and the reason is that I didn't pass any arguments. So this criterion was not satisfied, therefore, well, actually it was satisfied. It was not equal to 3, so it jumped inside of this code block and then exited early. So we haven't seen this exit function either. It's just used to jump out of the program prematurely. So now let's try passing 10 and 26.345. There we go. So argc is the desired value. It's 3, and we are now looping over argv, which is again just an array of characters. It's an array of characters. And the first argument is that // which is the name of our program, the binary. And then the second argument is the integer we passed, and the third argument is the floating point number we passed. And then finally, at the end, we are printing those as integers and floating point numbers, and not just as strings, to convince ourselves that we actually successfully converted them. And so now you can go crazy. You can change these to your heart's content. You can use negative, 23 and negative 21.345, and we successfully get that data into our program. So this is a really useful way to avoid rebuilding our code over and over and over again. So in general, if you're going to have parameters that you expect to change, you want to pass them from a command line or have them in some sort of input file and then read in the input file and read those values so that you don't have to recompile your code each time. Does that make sense to everyone? Okay. Moving right along to dynamically allocated arrays. So this is another important one, but it's pretty straightforward, I think. Essentially, a dynamically allocated array allows you to create an array in, as the name suggests, a dynamic way. So the idea is that if you don't know the size of your array, if you can't predict the size of your array, or your array is its size is going to fluctuate during the execution of your program, then you want to make it a dynamically allocated array as opposed to a static array. So a static array would be something like this. Whoops. Okay, so that's what we've seen so far with static arrays. With a dynamically allocated array, we're going to introduce a function called malloc, and malloc comes from actually, I guess you don't need any additional header files for malloc. I was thinking you did, but at least I didn't note that in the comments. If so, so malloc is essentially, it wants the size of your array, and it wants it in bytes. And so the way we give it the size is with the desired size of the array. So n is the number of elements we want, and then we multiply it times this size of function and the type for the array. So size of is another function that is brought in, it looks like not from a header file, but it's a function that we did not have to define. And all it does is return the number of bytes for a given type. And so it's going to return the number of bytes corresponding to an int, and then we're going to multiply that by n, and that's going to give us the total size that we're after. So all that's contained within this malloc call, and then we have to assign that to a pointer. And this kind of goes back to that definition of the pointer that I drew stars around earlier, where that first element is actually, or just just referring to an array in this way without any elements is actually an alias for the address of that first element. So when you are assigning a dynamically allocated array, it has to be declared in this way as a pointer. So we're going to set that equal to malloc, and now we can use it just like any normal array. All right. It's good practice to first make sure that you the malloc was successful. There's a couple of different ways. There's a function called assert that you can use to do that. But another way is to check whether if this malloc fails, it will assign the value null. So you can check to see if the value of your dynamically allocated array is null, if it's not pointing to anything. And if so, then we know that we failed and we should exit. But then, yeah, we could go crazy and just treat it like a normal array. So we're just accessing, we're looping over the array and accessing each of its elements and updating the value, and then printing the value as we're doing that. The only other thing you have to remember to do is to free up that memory. So I think this was a question that was asked, I think yesterday. If you use a dynamically allocated array, at the very end, once you're done using that array, you need to call this function free and then just pass the name of the array. I think that's all I wanted to say about dynamically allocated arrays. There's a difference between the type of memory that's used to store dynamically versus static arrays. But I would not really worry about that. It's not important to understand that for the purposes of this class. But if you're curious, you can Google like heap versus stack in C. So a dynamically allocated array is created on the heap, whereas a static array is created on the stack. And they have slightly different kind of performance characteristics. All right. Any questions at all?
So if you have like an array of size 10 and you wanted to like assign the 11th element something, does it know to like double the size of the array and then stick it in there, or is it going to like give you an error /fault?
It'll give you an error. So if you need to grow the size of your array, there's a separate function. It's not called malloc, it is called alloc. And so alloc allows you to dynamically add elements to the end of your array. And that's a good point. In general, with arrays in C, there is no bounds checking. So it does not do any sort of extra verification to ensure that you're asking for an element that you've actually been given by the program or by the operating system.
So you could end up like returning something that's actually not in the array, something at like the next address?
Yes. And in fact, I can show you. let's take a look at that, because this is something that can absolutely happen. And there are some pitfalls with malloc that definitely lead to some nasty bugs that are hard to track down. So let's see what happens. Actually, we haven't run this yet, so let's first just run it. Okay. Oops. Array size. Let's just make it 10 to be easy, and that's the output we get. Actually, let's make it smaller to make sure we can see this. Let's make it 3. All right. So now I'm going to, let's say, n plus 8 to make sure we really get outside. There we go. That's fun. So you can't quite see that. Yeah, there we go. Yeah, that's interesting. Look at that. Look at that. See that? So it's super interesting. How far did we go? To 10. Okay. So it looks like the interesting thing here, remember we were asking for only 3 elements, but after it gets past 2, it's still printing sane values. And the reason for that is that it just happened to use the same address space that we used the last time we compiled the program.
Oh.
So that's what's going on there. That might be, I'm sure that's confusing. That's the only reason. Because when we're assigning this is once we get beyond 2, it's undefined. It's completely undefined. So it's not as though this array actually exists. That's just a coincidence that we happen to get sane values after I equals 2. But once we got up to 11, it triggered. It tried to access something that was in some way clear enough to the operating system that it did not belong to our program. And so it gave us some really nasty error messages, and it mentions a core dump, which I won't really get into what a core dump file is. But if you see something like this, then your mind, or if you see an error message that says segmentation fault, the first thing you should think about is out of bounds errors. That you've miscalculated what your max array size is within a loop, or more commonly, what happens is people will copy and paste these malloc lines and forget to update the type. So like, let's say we wanted to dynamically allocate a float, and I was like, oh great, I've already got a malloc here, so this is going to be really nice and easy. I'm just going to say copy, paste, I change my type, and array float, and I'm good, I'm done. But you're not done. You forgot something very, very important, and that's to include a float here as well. All right, and so a float, as you can imagine, requires more bits to store, so it's larger than an integer. So if I leave this as an integer, it is not going to give me the correct size. But later in my program, I'm going to assume that I can go all the way up to n-1, when in fact the program hasn't actually allocated that memory for me. So that's a very common pitfall with malloc. So be really careful when you're copying and pasting mallocs, and double check your types and make sure that everything's consistent. Okay. Everybody good? Becca, Ray, you guys good? Okay, great. All right, last example. And then you guys are certified C pros. This is something that we will have to do within the class. And so basically I've just included this here for reference. I mentioned that sometimes rather than passing an argument from the command line, you might wish to actually define some variables within an input file, especially if you have a bunch of different variables that you're changing. If you have a list of 20 or 25, it's usually more convenient to do that within some sort of input file. And so my input file in this example is right here. I click on it, and this is what it looks like. So it's just 3 rows with 4 integers on each row. And so the point of, let's see, what am I doing here? So all I'm doing is, I guess, just grabbing the values from that file and then quickly assigning it to a variable and then printing the value of that variable. And so we're going to learn, this introduces the name of a new function called fscanf. And so fscanf allows us to read in a file. And you'll recall from printf that %d is the symbol used for an integer. And because we have 3 integers per row, we're going to have 3 %ds. And then we're going to assign that to x, y, and z. And you'll notice that we had to put ampersands out in front of those variables. Does that make sense? Why you would have to do that? Or does someone have an explanation of why we would need to have that ampersand? So without knowing much about how fscan works underneath the hood, we would still expect intuitively that remember, we're going to be entering into this function fscanf, and we want these values to propagate outside the scope of that function. So this is like a classic case of where we need pass by reference to ensure that the values that we come up with within this function actually make it out and are assigned to these variables and aren't just modified locally. So that's fscanf, and then we're going to print those variables just using a printf statement. Up at the top of the function, this is where we've defined kind of what the file type is. And so there's a type called file, all caps, and you need a pointer to that type. And here we're going to call it fp_in. Remember, you can have a space here if you want. Either way is fine. I tend to put spaces. And then we're going to assign fp_in. We're going to assign that pointer to the output of this function fopen. So it stands for file open. And all we do is pass the name of the file that we want to read. And in this case, we just want to read the file. We don't want to write to the file at all. And so we're just going to pass an R. So you can also write to output files. And that would be, you would put a W here instead. And then there's a separate function called fprintf that you would use instead of printf. So similar to with dynamically allocated arrays, it's good practice to check that this actually succeeded. If it does not, then we'll be, so if you gave an incorrect file name here, this would return null, and we would output an error message here and exit. So I've already kind of described this. Once we're done reading the file, we can close it using a function called fclose. And then below, we have an example of writing to an output file. So here, remember that this is specifying whether the file is read or write. So this is saying that we're going to write to this file. We check that this completed normally, and then we are going to loop over that. Actually, we're just going to, we're going to loop over 50 elements, and we are going to print out just the value of I and I times 10 on each row of that file. And when we're done, we close the file. So let's go ahead and run that. What was it called? File IO. And there we go. So the output we see in our standard output is from this line. So that shows that we just read in those values from this file. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you'll notice that we did not include the correct number of elements here. So we should actually, if we wanted to do this correctly so that we pulled off all of the values within the file, we would need an additional %d. I'm not sure why I did it like this. Probably just to demonstrate that it will still pick up at the end of that line and then go on to the next line if you don't get the appropriate number of fields right here. So you just got to make sure that you do that correctly. And then we also should have created a new file. Output. Yep, here we are. There we go. And there's our output file, which has the values that we expect. So that's how you work with files, either for reading them in to the program so you can use variables from a file, or writing out results. So writing out results is probably the more common case, and that's the case I think we'll see more within the class. Alrighty, are there any questions at all about that program, how it works? Awesome. Well, that is a wrap. That is all the examples I've put together. So at this point, again, if you feel comfortable with this content, you should be good to go. You should be in position to do well in the assignments in class that you see. I think seeing this a second time will hopefully just help cement it further. I'll also probably be moving at a faster pace within the class because there will be more questions, and so it's harder to kind of slow down and spend the appropriate amount of time on different pieces sometimes. so I really hope and I think that this will help you guys out in the long term, and it'll kind of give you one less thing that you have to learn at the beginning of the course, especially if you're not familiar with using Linux or Git. If you come in without Linux, Git, or C, it can be a little bit overwhelming within the first few weeks. So I guess unless there are any other questions, we can wrap up, and I'll see you guys on Monday for the first day of class. Are there any lingering questions at all? No? Okay. All right. Well, thanks a lot for participating, guys. And I will see you all on Monday. Stay warm.